slides, and of course the same topics are treated in your textbook as well in a slightly different way. And my suggestion is, if you follow along what's in these slides, and if you understand everything that's in there, you don't need to read the textbook, okay? So that'll alleviate some of your difficulties. Copies of these will be posted online, so you can actually go back and look at them as well. So this is due to Jim Orlin at MIT, who's one of the co-authors of the textbook that I brought to class the last time we met. Okay, and it's also part of the MIT Open Courseware Initiative with a lot of material that's available, and this is particularly nice, so I thought I should use this rather than redo something that's already out there. Okay? So the topic is the maximum flow problem. We discussed it in the first lecture on network flows, along with several other problems. And today we are going to explore an algorithm to solve this problem, as well as certain consequences of the correctness of that algorithm. And if time permits, we'll also get into applications. And these are applications not necessarily to real-world problems, but also applications to other aspects of theory, mostly graph theory. So you'll see certain results that can be proved very easily using the max flow min cut theorem. Okay. So here's the problem itself. So you're given a graph G. The xij's we'll use to represent the flow on arc ij. Okay. So as always, we look at what are called directed graphs. So you have nodes and you have arcs, which are edges with directions. Every arc has a certain capacity, uij. That is the only relevant parameter for on the arcs. Okay, so there are no costs. There are only capacities. You have a source node S and a sink node T, and the question is, find a way to shift as much stuff as possible from source S to sink T, and the only restriction is that you obey capacity constraints. Okay, so your linear programming problem looks like the following. You'd like to maximize V, which is the value of the flow. This is the amount of material that travels from S to T, subject to the following constraint: that flow is conserved at every node other than S or T. So the way you read this is the total amount of flow that leaves node I, which is the sum of all xij's, which is summed over all the j's. Okay, so this is the amount that leaves node I equals the total amount that enters node I. Now obviously this must be true for every node I other than the source of the sink. Okay? And of course the total amount that leaves the source has to be V, and you'd like to maximize this value. Okay? And these are the capacity constraints that all the flow values obey the capacities on the arcs. So we didn't say that those V units that leave node S reach node T. We didn't explicitly state that as a constraint, but you can easily work out and observe that if V units leave node S, and if flow is conserved at every node other than S and T, then those V units have to reach node T because they don't have anywhere else to go. Okay? So you can write the maximum flow problem as one of maximizing the amount of flow that leaves node S, or maximizing the amount of flow that reaches node T. And these two are equivalent as long as there are no gains in your network. Okay? If arcs have gains, meaning flow gets transformed, multiplied by a factor bigger than 1 or smaller than 1, then of course the stuff that leaves one end of an arc is not equal to the stuff that reaches the other end, and then you don't have this equivalence. Okay? Any questions about this formulation? So this is just a simple linear programming formulation of the maximum flow problem, and therefore we can use the simplex method to solve it. Okay? The goal of this lecture is to look at other methods, in particular what's called the Ford-Fulkerson method for solving maximum flows, or for finding maximum flows. Okay? So anyway, that's the definition of a maximum flow. So a flow is just, specified by specifying the amount that flows in every arc. And if it is it's maximum if it maximizes that value V, the amount that leaves the source. Okay. So here is a little example. So the red numbers indicate the current flow values. I guess the black ones indicate the capacities. And here is a flow of a certain value. So the value of this flow is actually 13. Okay. Because 13 units leave the source. Is this maximum? Clearly no. Why?
As you see the flow out of S and flows into T, so the flow path, the flow path leading S and flowing into T are not maximum.
Or in other words, there is a way to actually send, what's the easiest way to observe that this is not a maximum flow? Well, finding one that has larger value. So for instance, I could send one extra unit from S to 2 to T. Okay. And so that will give me a flow with a larger value. Right? Everyone comfortable with this? Okay. So this is a non-optimal flow. Now, first of all, it's so let's look at a few little applications, baby applications. Okay, so here you have warehouses and retailers, and there's a connectivity graph. Okay, so that says that warehouse is linked to the corresponding retailer. So from warehouse 1, you can ship to retailers 6 and 8, but not to 7 directly. Okay, or to 9. From warehouse 3, you can ship to any retailer except node 7, and so on. Now these could be the supplies at the various warehouses of a certain commodity, and these could be the demands. And the question is there a feasible way of sending the supply to satisfy all the demands? Okay. Is this question clear to everyone? So we just want to find a way of sending flow such that all of the demands are met using the supplies that exist. Okay. And as you can see, the total demand is 24, the total supply is 24. So how would you view this as a maximum flow problem? There are no costs. We just want to find a flow satisfying all the demands. Does anyone see a natural max flow problem that can solve this? Well, we could construct a single source. Okay. And we could construct a single sink. Okay. So I've just added 2 extra nodes, the source node and the sink node, and I added all these extra arcs, the blue ones, that go from the source to each of the warehouses and from every retailer to the sink. And the capacities are exactly the demands here. The capacities of the source to warehouse arcs are exactly the supplies. Okay. And suppose I solve a max flow problem on this network. If my maximum flow has value 24, which is the sum of all of these, then there is a way to ship the commodity to satisfy all of the demands. And if the maximum flow value is less than 24, then there isn't. Okay? And this should convince you, just a little bit of thought should convince you that these two observations are easily proved. If there is a flow with value 24, well, because these are the capacities and the total capacity is exactly 24, I should be able to send 6. The only way I can get a flow with value 24 is if I send 6 units along this arc, 5 along this, 4 along this, and so on. Okay? And the only way for me to receive 24 units here is for this node to send me 6, this node to send me 7, this to send me 6, and this to send me 5. But the only way this node can send me 6 units is if it receives 6 units, and so on. Okay? The arcs in the middle, the red ones, have infinite capacity, so they don't play any role in limiting the maximum flow. Okay? Of course, if there is no way for you to send 24 units in this network, then the original problem must have been infeasible. Okay? Because any feasible solution to the original problem would translate to a flow of value 24. So, so basically, if you look at a transportation problem with no cost, only feasibility, that reduces to a maximum flow problem. Okay? Any questions about this? Yes. Is this problem feasible? Well, let me see.
It doesn't seem to be feasible.
Why doesn't it seem to be feasible?
Well, house 2 and 4 only have an outlet to retailer 7.
Mm-hmm.
And they must receive the maximum capacity.
Mm-hmm.
That'll be 10 altogether for warehouse 4. 7 can only have 7.
Okay. Well, that's a very nice observation. So if you look at nodes 2 and 4, any flow that they receive can only be forwarded to node 7. Okay? So 2 and 4 cannot reach any other retailer. So retailer 7 has only a demand of 7, okay? Whereas 2 and 4 together have a supply of 10. So 3 extra units from 2 and 4 cannot be sent. Okay? Therefore, you cannot achieve a supply of 20. You cannot achieve a max flow of 24. Okay? So whenever you have a certain subset of nodes such that their cumulative supply cannot be forwarded to the nodes on the right, you cannot pump all of the flow. Of course, this would be an incomplete argument if the total supply here had been 85 or something, and the demand were only 24. But here, the total supply is 24, the total demand is 24, so anything that cannot be sent from a certain node means that some demand cannot be met. Okay? So this shows that this particular network does not have a feasible solution, the transportation problem. Okay? And we may come back to this kind of reasoning if time permits towards the end of the lecture. Okay? So keep in mind exactly how this proof of infeasibility went on this little example. Any other questions? Okay. So here's another problem which is not unrelated to what we just saw, which is that you have a set of people and you have a set of jobs, and each person can do a certain subset of jobs. So for instance, person 1 can only do job 6. Okay. 3 can only do job 6. Okay. 2 can do 7 or 8. 4 can do 6, 7, or 8. Two can do 5 as well. Okay. So again, the question is, can you match people to jobs such that every job is assigned and every person is assigned? Here we have the same number of persons and jobs. You could think of a situation where there are more jobs than people, in which case you want to match every person with a job, and at most one job per person, and the symmetric case as well. Now here again, for the same reason that was pointed out, there is no matching. There is no way to assign every person a job and every job to a person, because if you look at agents 3 and 1, both of them can only do job 6. So, and of course only one of them can be assigned job 6, so one of them must be unassigned. And because there are the same number of people and jobs, one of the jobs must be unassigned as well. Okay? But in general, you could have a bigger graph, and you would like to know whether there is an assignment that satisfies all of these properties, that at most one job is assigned to every person, and at most one person works on every job. And in general, you may want to find an assignment that maximizes the number of jobs assigned, or maximizes the number of people assigned to jobs, if you can't assign everybody. And exactly the same idea works. So for instance, we could give you could create a source node S and give each of the people a supply of 1, and similarly each of the tasks has a demand of 1, and you find a maximum flow. So if there's a flow of 4 units, then you have a feasible assignment, and if there isn't, then you don't. So this is yet another sort of quote-unquote application of the maximum flow problem, that if you want to find a matching in a graph, that's the structure that we were looking for, then you could solve it as a maximum flow problem if the graph is bipartite. Okay, so in computing maximum flows, there's a certain structure that's useful, which is called the residual network. Okay? Your textbook does not develop this notion, but works with it implicitly. But it's actually useful to think about maximum flows in terms of these quantities. Okay? So I'll find you some other readings if you're interested, but for now, just the slides would suffice. Okay? So we go back to this example that we saw, and we saw that this was suboptimal, right? You could send an extra unit along the bottom path from S to 2 to T. And therefore, this is not a maximum flow. So how might an algorithm to compute maximum flows work? So one natural idea might be the following, that you start with some feasible flow, just like a flow that's in there, which respects all the capacity constraints, and you try to improve it. Okay. If you can improve it, then you go to another feasible flow. And keep doing this until you can no longer improve the flow, and hopefully you'll end up with an optimal one. Okay. These are what are called augmenting path methods, because the only way for you to improve a flow is to find a path from S to T along which you can send an extra unit, a path along which you can augment the existing flow. And that's why they're called augmenting path methods. Okay. So how would you, so we already saw that in this particular network, the way to improve the flow would be to send one extra unit along the path S to 2 to T. You could also send one extra unit along the path S1T. Okay. That's another augmenting path. And the question is, can you figure out a way to detect augmenting paths? Can you figure out ways to improve the existing flow? And for that, it's useful to draw what's called a residual network. And the residual network is shown in the bottom. So let me explain how you get this. So one thing to keep in mind is that the residual network is always defined with respect to an existing flow. It's not just a function of the given network, it's also a function of the existing flow. Okay? So let's look at this arc from S to 2. Okay? From S to 2, the original network has an arc of capacity 6, and the existing flow on it is 5. Okay? So we want the residual network to capture ways in which the current flow can be modified. Okay? So there are a bunch of things we could do. We could increase the flow along this arc S to 2. Okay? So if you look at this arc, the extent by which you can increase the flow is actually just its residual capacity, right? So this arc has a capacity of 6, a flow of 5, so I could increase it by up to 1 unit. That's going to be the capacity of the forward arc. Okay? Now we could also modify this flow in a different way. Right? We could send fewer than 5 units along that arc. Okay? Now why would you want to do that? Well, maybe you discover an augmenting path by rerouting the existing flow in a certain way. Okay? So for now, keep in mind that there may be modifications of the existing flow that may involve sending less on a certain arc and more on some other arcs. Okay? So far the modifications we've looked at always increase the flow along an arc, but there could be situations where you may have to decrease the flow along certain arcs. And for that reason, there's a backward arc. This goes from 2 to S with capacity 5. Now, this represents the opportunity that you have of decreasing the flow along the arc S2. And this says I could decrease the flow along this arc by up to 5 units, and I still would be okay. If I decrease it any further, of course, I'd be infeasible because I'd be violating the lower bound constraints. Okay? So this just represents all the opportunities you have of modifying the existing flow. So that's why the forward arc has a capacity of 1, and the backward arc, which goes from 2 to S, has a capacity of 5. Okay? And the same for every other arc in the network. So if you look at the arc 1 to T, the forward capacity is 1 and the backward capacity is 7. Likewise here, there's 4 and 6, and likewise here, 2 and 8. And if you look at this arc that goes from 2 to 1, actually if you look at the original arc from 1 to 2, in the forward direction it's saturated. Okay? It has a capacity of 1 and 1 unit is already sent. So there is no way for you to send anything from 1 to 2. You cannot use that arc in that direction any further. So we could draw that arc with a capacity of 0, but we just choose to omit it. Okay? Whereas you do have the opportunity to decrease flow along that arc, and that's represented by this arc. Okay? So given any network and an existing flow, you can construct what's called a residual network, whose forward capacities are the amount of spare capacity in that arc, and whose backward arcs have capacities equal to the existing flow. Okay? And anything with a value of 0, you omit, you don't draw. So in this case, there's exactly one arc with that's saturated, so in the forward direction it had a 0 capacity, so we just don't draw it. Okay? This is the critical concept in coming up with algorithms for maximum flows, at least the algorithms that we'll work with. Okay. So if there are any questions, please ask me now.
Each forward arc has a difference between the capacity and the current flow we have now. But I don't understand for this case, the case of the arc from 1 to 2, you put away the forward arc because
it has capacity 0.
Yes, for the difference, right?
Right. Okay. So if it has capacity 0, we can't use it to do anything, right? It cannot carry any more flow. Similarly, if some arc has 0 flow, then the backward arc will not exist because you cannot decrease flow any further. Okay, so this example, none of the arcs had 0 flow, therefore. Any other questions? Okay, very good. So that's the residual network, and here's the illustration. So if you have an arc with capacity Uij and flow Xij, then in the residual network, where the nodes are in yellow, you have a forward capacity of Uij minus Xij and a backward capacity of Xij itself. Okay, so here are some definitions. An augmenting path is a path from S to T in the residual network. Okay. And the capacity of the augmenting path is the smallest capacity of the arcs in the residual network. Okay. All of these definitions will make intuitive sense once you see one step of the algorithm. So, what does it mean? So, if you find a path in the residual network, that gives you an opportunity to increase the flow from S to T. Okay. Now, you're going to increase it by the residual capacity of that path. Okay. So, if I have a path in which one arc has extra capacity 5 and another arc has extra capacity 7, then I could increase flow by up to 5. But if I try to increase it any further, then there is this arc that cannot carry any more flow. Okay. That's the reason why you look at the minimum capacity arc in this path. That's defined as the residual capacity of the path. Okay. And to augment along P is to send exactly this amount along every arc of the path. Okay. Now, once you augment flow, the existing flow changes, and therefore the residual network is going to change. Okay? So the way the algorithm we have in mind is going to start with some feasible flow, find the residual network, find an augmenting path, and modify the flow, and repeat this until we cannot do this anymore. Okay? So that's the general algorithm, and this is how the residual network gets modified. So you will see a little illustration. So for instance, so here is the augmenting path of that example that we just illustrated, and let's look at some path in the residual network from S to T. Okay? So how will you find a path from S to T? Well, you start at S and do a breadth-first search. Just explore all its neighbors and all its neighbors' neighbors and so on. And eventually, if you succeed in reaching T, you have a path. Okay? So it's basically looking at some version of breadth-first search. There are simple labeling strategies that will get you this as well. Now, on these examples, you can just discover paths just by eyeballing. So let's pick the following path. Okay? So the red path, which goes from S to 2, 2 to 1, 1 to T. That's the path in the residual network. Okay. So what is the residual capacity of this path? It's actually 1, because every arc here has capacity 1. Okay. So you're going to send 1 extra unit of flow along this path. Okay. Now, what that does to the augmenting path, what that does to the existing flow is that there's 1 extra unit here, 1 extra unit here, and 1 extra unit here. Okay. Now, how will the residual network get modified because of that? Well, for that, you have to go back to the original network and see what happens to this new flow. What is the value of the new flow? You will observe that, of course, arcs that are completely untouched by this modification just stay the same, right? So that's arc 2T and arc S1, their residual capacities don't change at all. Whereas if you look at the other residual capacities, you will see the following. So recall that this in the original network was an arc from S to 2 carrying a flow of 5. Now you're sending 1 extra unit of flow, so it's going to carry 6 units of flow, and it's going to be saturated, so it's up to capacity. Therefore, the forward arc is going to have 0 capacity, so you don't draw it, and the backward arc is going to have extra 1 unit of capacity, so it has capacity 6. Okay. Likewise for this one. Okay. So this in the original network ran from 1 to t with a capacity of 8 and flow of 7. Now you send one extra unit, the flow becomes 8. So the forward arc drops out and there's a backward arc with capacity 8. Okay. And the interesting thing is this arc here, which if you recall was sending 1 unit of flow and had a capacity of 1. Okay. Now you're sending that 1 unit in the opposite direction. So that means you're decreasing flow along the arc by 1 unit. Okay. Therefore, if you redo the residual network, that arc is now carrying 0 flow in the original network. Therefore, its residual capacity is 1 in the forward direction and 0 in the backward direction. So we omit the backward arc. Any questions about this?
Feasible? Is it feasible?
Is it feasible?
How do you conceptually understand that you are not sending anything to the arc that's going to and 1 and eventually getting a T? That extent.
No, so this is just how we are modifying the flow and constructing the new residual network. Okay. Before we were sending 1 unit from 1 to 2. Now it's as though we are sending it back. So it's as though we are not sending anything from 1 to 2 at all now. Okay. So yes.
Like how confused about the value R, I, J, and what's that?
You mean these updates?
Yeah, these updates.
Okay. So right now, don't look at that. Just understand what I'm trying to say. Okay.
If you just arbitrarily choose that path, you could have gotten something you could tell
That's exactly right. So I just picked this path from S to 2, 2 to 1, 1 to t because I wanted to show how this cancellation could occur. But we could pick any path from S to t, and we'll have a little more to say about it, in about 20 minutes or so. Okay. Don't look at the update for now. Okay. That assumes a certain convention that I did not discuss, and so you can just ignore it. The only thing for you to keep in mind is that the residual network, the residual capacities can be updated just by observing what happens when you augment the existing flow along with this new flow along that path. Okay. Any other questions? Okay. Now, what do we do next? Well, we again check if there's a way for us to reach T from S in this residual network. Okay. Maybe let's actually just finish that example. So here, is there a way for you to reach T from S? Well, you could go from S to 2, S to 1, 1 to 2, and 2 to T. Okay? What is the capacity of that path? Again, it's 1 because this is the bottleneck arc. So you can send at most 1 unit of flow along that path. Okay? And if you do that, what's going to happen? What's going to be there? Let me draw the new. So here is S. Here is 1. Here is 2. And here is T. Now, the augmenting path is going to be S to 1, 1 to 2, and 2 to T. Okay? We are going to send 1 unit of flow extra from S to 1, 1 to 2, and 2 to T. So just keep that in mind. And I want to draw the residual network. Well, first of all, these two arcs are untouched. Okay? So their residual capacities are going to stay exactly the same. So this is going to have a capacity of 6. And this is going to have a capacity of 8. Okay? Nothing changes. Then, S to 1 has a residual capacity of 2. We are going to send 1 extra unit. Okay? So the forward capacity is going to become 1, and the backward capacity is going to become 9. Okay? Is everybody comfortable with that? Similarly, from 2 to T, you're sending 1 extra unit, so the forward capacity becomes 3, and the backward capacity becomes 7. Okay. And from 1 to 2, remember, in the original network, there was an arc from 1 to 2. Okay? And the fact that in the residual network, the same arc exists with capacity 1 means that we are not using that arc at all in the current flow. Now we are sending 1 extra unit. So this arc is going to be saturated. Okay. It's going to carry 1 unit, and it's going to be up to capacity. So the forward arc is going to have capacity 0, and the backward arc is going to have capacity 1. And because the forward arc has capacity 0, we omit it. Okay. I see some unhappy faces, so yes.
Why don't you update the other like 2 arcs like 6 and 8? Like you got that like downward 1 because you updated the 6 and 8 by adding 1 to the capacity.
Mm-hmm.
And then now you just like reversing the capacity between like 1 and 2. And then any reason that we don't update those 2 arcs?
Any reason why we don't update these 2? Well, the current augmenting path, which I have not drawn here, is S to 1 to 2 to T. Okay? So when I send 1 extra unit of flow along this path, these 2 arcs are not involved at all. Right? So their flows don't get modified in any way. So their residual capacities are going to stay the same. Okay? So let me put it to you in a different way. Okay? So let's look at this network S 1, 2, T. This is the original network, okay? And the current flow is actually the following. No pens. So the current flow is that there are 6 units here. Okay. There are 8 units here. There are 8 units here, and there are 6 units here. Okay. That's the current flow. Okay. The capacities are 6 for this arc, 10 for this arc, 8 for this arc, and 10 for this arc. Okay. So this arc has capacity 10, current flow 8, capacity 6, current flow 6, and so on. Okay. This has capacity 1, and the current flow is 0. That's the current flow. For this flow, this is the residual network. Okay. Now we are augmenting this flow by sending 1 extra unit along the path. This, and this. Okay. So when you do that, what's going to happen? Well, this flow is now going to become 9. This flow is going to become 1. This flow is going to become 7. Okay. And now, what I've drawn here is the residual network corresponding to this flow. Which is exactly this. Okay.
It's kind of confusing. Like before, like in the original network, you really don't have like any paths like to go from like 2 to 1.
Yes.
But in the religion network, you somehow like figure out like you can go from 2 to 1.
Remember, the residual network only captures the way, all possible ways in which the existing flow can be modified. Okay? So what does it mean for this arc to exist at capacity 1? It means that the current flow sends something from 1 to 2, and you can not send, so you can change the current flow by rerouting that unit from here to somewhere else. And that's what this arc represents. Okay? So the residual network captures all opportunities you have of modifying the existing flow. And therefore, it will exist, this arc will exist only when you're sending flow from 1 to 2. Okay? If you're not sending anything, well, you cannot withhold or reroute flow along that arc. So in this particular flow, you're not sending anything. Therefore, that arc does not exist. Okay? Whereas here, you are sending something, and therefore that arc does exist. Okay? So as we go along, it will become even clearer. But just bear with me for a moment. Okay? So this is the residual network corresponding to the current flow. And now again, you can ask whether there's a path from S to T in the residual network. And the answer is, I hope no. It is no, right? I mean, from F, so from here, I can reach node 1, and that's it. Okay. So therefore, we stop. Okay? How do we know this is the maximum flow? Well, we don't, not yet. Okay? But here's one way to see it. So from S, let me look at all the nodes that I can reach. So here from S, I can only reach node 1. Then I just look at nodes S and 1 as a group and see how much capacity there is. Okay? So let's go back to the original network. You can see that if you take S and 1 as a group, together they have, look at all of the arcs that take you from that group, from nodes S and 1 to outside of that group. Okay? So this arc has capacity 8, this has capacity 1, and this has capacity 6. Okay? So totally you have a capacity of 15. Okay? So certainly anything that travels from S to T has to use one of these arcs, right? Because S is in this group and T is outside the group. So it has to cross